Okay, I welcome everyone. Thank you for joining our online machine learning technique class. So I hope everyone is doing good. So we had some discussions last week, mainly on the preliminary discussion regarding supervised learning, and we had a chance to look into some implementation in Google Colab. So we have seen some basic Python code in Google Colab platform. So today we'll start from previous, that's supervised learning, and we'll try to understand the model today. We have seen linear regression model. Today we'll discuss about classification model, that is decision tree. So are you aware of decision tree? Do you know? Have you heard decision tree algorithm before?
Yes, sir.
Decision tree algorithm is classification algorithm. There are quite a few classification algorithms. Decision tree is one of them. Along with decision tree, there is support vector machine, there is artificial neural network, there is naive Bayes classifier. So decision tree is very widely used and a very old model. For some data set, it gives good output. So it's kind of tree-based classification. So we'll try to understand this today. At the end, we'll try to cover some machine learning libraries, that is NumPy and Pandas, in the Google Colab. Okay. Let me share my screen. Is my screen visible?
Yes, sir. It's visible.
Okay, it's from week 2. So the lecture starts with some previous discussion that we have already discussed in our early classes. For example, what is learning? And we had seen some definitions regarding learning before. So in terms of basic programming and machine learning programming, what is the main difference? We do programming, right? But what is the basic difference between normal programming and machine learning programming? Can anyone tell me? What do you think? Just in your own words. It hasn't to be anything from document or any book. What is your opinion about this? What is the difference between basic programming and machine learning programming? Anyone? Well, in terms of basic programming, what happens, we give some input and we get some output, and that's all. The machine learning, it is continuous process. We give some input, we get output, and we evaluate output. And based on evaluation, we again revise my input so that we can improve my performance, improve our performance. Does it make sense? In basic programming, there is no chance of improving your output. improving your experience. Got it? As simple as that. In machine learning programming, depending on output, we revise input so that we can improve our output. There is the effort to improve our output in machine learning, but in basic programming there is not. Is that clear?
Yes, sir.
Okay. So this is a very basic definition, and we have some definition for learning. We have already seen these, just skim through. So what happens? Learning is something that is related to real world, you know. For example, you know how to make a cup of tea. You know that is a knowledge, but that is not learning. Until and unless you go to the kitchen and start making the tea with tea bag, sugar, milk, cup. Until and unless you started making the cup of tea, you are not learning. But you know how to make it. But that is not learning. As soon as you start making the cup of tea, then you started learning. Get it?
Sir, without learning, how can I know that?
Sorry? You can know from any previous algorithm. You can know it. But you cannot improve. The moment you started learning, you have a chance to improve. For example, you put 1 spoon of sugar, but that is not tasty. When you taste it with 1 spoon of sugar, you feel like you are not happy. So when you come again in the kitchen and making second cup of tea, so you put 2 cups of sugar. You got it?
Yes, sir.
That means now you have learned. I'm giving just an example, but it's like that. Until and unless you are in the real world, or you're not applying your algorithm, you're not basically learning. Until and unless we apply our algorithm on a data set, the algorithm is not improving. Right? So we use our data to basically improve the learning experiences of our algorithm. Right? So that's kind of a concept about learning. Okay. So here is how we can actually gain knowledge in terms using data, right? There are some learning parameters, Bayesian network graphs, and clustering. These are some technique that we can use to improve our learning experiences. So we have already seen this. We have quite a few categories in terms of learning. We have supervised learning, we have unsupervised, and we have semi-supervised, and we have reinforcement learning. We have discussed this before. We know what is supervised learning, and we know what is unsupervised learning. These two are the most commonly used terms in machine learning paradigm. Okay. So what is supervised learning? What happens? In supervised learning, basically, the target level is known. In unsupervised learning, target level is not known. That's what we have seen in our early classes. Okay. So what happens in supervised learning? We have some data, we have some features that we call attribute or parameters, and we do some experiment, that is training and testing. Then we have testing and evaluation phase, and finally we try to generalize this. If we have any overfitting issues, we try to generalize this. So that's a sort of standard procedures in terms of supervised learning. Okay. So let's see an example about email spam filter. I believe that all of you have received in your lifetime a spam email in your inbox. You may have noticed that there are some spam emails in your spam folder, sometimes in your inbox, and you manually forward it to the spam folder. Now the email system, email mechanism is getting smart, so they can recognize that which email is smart and which email is a spam and which email is not. So depending on their understanding, depending on their some intelligence, so they basically automatically forward the spam email to your spam folder. So it will prevent the spam emails to directly go to your inbox folder. Did you notice that?
Yes, sir.
So how the system, email system, does this? Do you have any idea? How the system understands that this email is a spam and this is not?
I think the system might check out or look out for particular words that could be related to spamming in my email.
Sorry, I didn't get you.
I think the email system look for particular phrase or words in my email text that could be related to spamming.
That's true. That's true. So if it is spam email, it basically uses a set of words, typically that helps it to recognize that this email could be an spam email. Okay. So here we have some examples. For examples, words free. If you find any word like this, free, in your email, or the email system recognizes there is an email that contains this word, so it automatically forward the email to your spam folder, or something like this dollar symbol, caps symbol, all letters are capital. Okay. So for example, this one, you see, this one is considered as a spam and this is not. Okay. So the systems is continuously learning depending on the emails sent from anonymous people, and it basically improving itself so that it can recognize that which email is spam and which is not. Because just imagine that your email is overcrowded with a spam email. Your inbox is overcrowded with a spam email. So do you think you will be interested to use that email account again?
Never, sir.
If your inbox is full of spam email, never, right? So it is very important for the email account provider. For example, we use Google to recognize the spam email because they're connected with their business. Okay, because if we do not use their email, so they cannot make business, right? There's another application that you can think of, which is digit recognition. Yeah, you see, there's some digits, and we want our machines to recognize these. So handwritten digit. So this is 0. So machine has to say that this is 0. So this is 1. So machine has to tell that this is 1. So, but handwritten is different if we go from one person to another, right? We all have our unique style of writing, right? Handwritten. But whatever it is, I can understand as a human, I can understand even if it is handwritten of many people's, right? If it is the known language to me, right? But my task is to whether the machine can understand it or not. Okay. So this is another interesting application of machine learning. So there are some other areas that we can apply classification, so medical diagnosis, OCR, fraud detection, DNA protein analysis, astronomical images, categorization of astronomical images, and so on. A lot of areas that we can use our classification technique. So our target is to learn decision tree. So before that, we are just trying to understand some parameters, terminologies that will help us to learn the tree at the end. So we have inductive learning. So what is inductive learning? Let me explain. So when you learn a function from examples, that is basically inductive learning. Okay. So when you say that learn from a function, from examples, learn a function, what does that mean actually? For example, we have a data set and we have some class levels, that is playing games, yes or no, and we have some attributes, right? So here the function is basically the model. So if you can train our model with this data, that if the conditions are like these, then there will be play, and if the weather condition is like this, there we cannot hold any play, right? So playing yes or no is depending on some parameters, weather conditions. Okay, so basically we are learning from some examples. Here examples means the data, right? So we can refer that to inductive learning. So more precisely, if we consider that f is a target function, what is target function? That is our class level. Okay, that is the function. So we are basically using this function for prediction, basically, mainly. Yeah, for example, we are giving an input, particular input x, and we're trying to predict that function of x. For example, let's say x is a temperature. Okay, and now we're putting this temperature into this function to inform me that whether there will be play or not. So when I'm giving a particular temperature as x into this function, the function's duty is to inform me, to tell me whether with this temperature we can play the game or not. Got it?
Yes, sir.
Okay, so that is basically we are learning depending on some input. Okay, some example. Here x is an example. You see, from example, here x is an example. And function, this is the function. Okay. So what happens, we basically make a hypothesis depending on this learning, that is age, and most of the cases we expect that H is equivalent to F. Yeah, H is a hypothesis and which is equivalent to F. But when what happens if our hypothesis is matches most of the time with the function, then we can take that hypothesis. Okay. Otherwise, that hypothesis will not be in action. For particular training data, right? So we make a hypothesis. You see that in our previous classes, we tried to explain some models. We drew some patterns, and we have perfect model, and we have some models that is close to the perfect. Did you remember? So hypothesis is basically not the perfect function. Is not the perfect function. That is F. F is the perfect, and H is not perfect. But our target is to make this H hypothesis as close as to the function. Okay, that's why we are generalizing. We are generalizing the function. Okay. So if our hypothesis that our algorithm is making, if it is close to the F, because F is giving you just exact value, right? You are giving X, and F is giving you a value which may be true or may not be true, right? But you get a value. But H, it's just a hypothesis. That means it might go. You have 2 points. It might go in between the points, right? So H will never guarantee you that it always touches the data points because it is a hypothesis.
Sir, if our hypothesis is correct, then whether it could be H equal to F, is it possible?
It is very difficult to get this kind of hypothesis because in real world, if it is equal, that means you are talking about 100% accuracy. But in real scenario, it is very difficult to get like that.
Yes, sir. Yes, right.
You got
sir.
it? Because if it is equal, that means it's 100% accurate. But in real world, it is not like that. It's more complex than that. Yeah. Okay. So we have an example here. So you see there is some data point here. So H is consistent if it agrees with F and all examples. You see, we can say that the hypothesis is consistent if it agrees with F on all examples. That means if our hypothesis is true for all the data here, then we can say that the hypothesis is consistent. But in real world, it is very difficult to find any hypothesis that is consistent. Clear?
Sir.
Yes.
Sir, বাংলায় বলি স্যার। হ্যাঁ স্যার, যেমন আমরা
বলেন।
অডিও সেন্সর ব্যবহার করি, অডিও সেন্সর ব্যবহার করে ধরেন আমরা চাচ্ছি দরজাটা খুলে যাও, আমি যদি বলি যে খুলে যাও, তো এখন আমরা যে কথাটা বলি আর ওখানে এই প্রোগ্রামিং এ যে ল্যাঙ্গুয়েজটা দেওয়া আছে সে যতটুকু বুঝতেছে আমাদের কথার সাথে অ্যাডজাস্ট হচ্ছে না স্যার, বা অ্যাডজাস্ট কতটুকু হচ্ছে সেখান থেকে সে একটা ধারণা করে জিনিসটা খুলে দিচ্ছে স্যার। এটা কি এই আমাদের এই টপিকের সাথে পরে কি?
হ্যাঁ হ্যাঁ, অবশ্যই, ডেফিনেটলি এটা পড়ে। এটা স্পিচ রিকগনিশন হিসেবে এটা হবে আর কি। ঠিক আছে, সেক্ষেত্রে যেটা আপনাকে করতে হবে, মনে করেন আপনি বলছেন আপনার বাসার দরজাটা খুলে যাক আপনার কথা অনুযায়ী, তাহলে কি করতে হবে, আপনার ভয়েস, আপনার টোন, আপনার ফ্রিকোয়েন্সি গুলো অনেক ভেরিয়েশনের স্যাম্পল নিতে হবে, নিয়ে ট্রেনিং করতে হবে সেটাকে অ্যালগরিদম দিয়ে, ঠিক আছে, যাতে সে বুঝতে পারে যে এটা আসলে আপনি, মানে প্রথমে আপনার ভয়েসকে চেনাতে হবে মেশিনকে, ঠিক আছে। তারপরে যখন মেশিন চিনে যাবে তখন আপনি যেটাই বলবেন মেশিন তখন ওইটা ফ্রিকোয়েন্সি, আপনার ফ্রিকোয়েন্সি এবং আরো কিছু প্যারামিটার নিয়ে সে এটা বলতে পারবে যে এটা আসলে আপনি, ঠিক আছে। সেই অনুযায়ী তখন সে টাস্কটা অ্যাকমপ্লিশ করবে।
থ্যাংক ইউ স্যার।
Okay, so we have some data point here. So first of all, we tried to put it a straight line here, but you see if I put a straight line, some data points are missing here. One is here and one is here, right? So it is not consistent. So then we try to draw a curve like this, non-linear. So it touches all the data points except the one, this one, right? So we can say that this curve, non-linear line model is better than the straight line, right? If we want to touch all the points, then we have a curve like this. But do you think that this is good? This can
No,
be a
sir,
good
it's
one?
overfitted, I think.
It's overfitted, right? So this is not good. Again, we can do like this, zigzag. Again, these might not work well for testing data. It might work well for training data, but not for the testing. Okay. So depending on this scenario, what actually we try to do, we try to generalize this. Okay? We try to generalize this one, and this one. We try to generalize. So in terms of generalization, there is a principle of Occam's razor. So he said that we try to pick the simplest one, simplest hypothesis we try to pick. So out of these 3 or 4 models, we try to pick the simplest one. Which one is simple? We try to do that. That is a kind of generalization. Okay. And there is, we have seen this plot before. It's basically a prediction error.
Sir, I had a question.
Yes.
Sir, if we choose the simplest one, then our hypothesis won't be that much accurate with F, right?
Yeah, that's true. We can explain it here from this plot, because it cannot be the most simplest. It could be somewhere in between. Then we can basically improve the accuracy. For example, you see we have along the y-axis we have prediction error, and along the x-axis we have model complexity. Yeah. So when the model complexity is very low, our prediction error is very high, right? Both for test and training data.
Right, sir.
This line is training and this red line is testing error. Yeah. So when we are increasing the model complexity, the prediction error is decreasing, right? Model complexity we are increasing like this from low to high. The prediction error decreases, right?
Right, sir.
Model complexity slightly increases, the prediction error decreases for both samples, training and test. But if you notice, after a certain threshold, when I increase the model complexity further, the prediction error for training sample, it continuously decreasing, but for test sample after certain period it started increasing. Did you notice that?
Yes, sir. Middle point.
That means the model complexity should not be very low or very high. It should be somewhere in between. That's why we are generalizing. Got it?
Yes, sir, got it.
Now, can you tell me, when the model complexity is low, which issue we face, and when the model complexity is high, which issue we face between overfitting and underfitting?
When the model complexity gets low, we face the bias high and variance gets low.
No, that's good. We have this, it's already mentioned here. But in terms of overfitting and underfitting, when model complexity is very low, in these circumstances, prediction error is very high, right? For
Right.
both of the sample. So this is overfitting or underfitting? That's what my question was.
Underfitting, sir.
Underfitting, exactly.
Underfitting, sir.
This is underfitting. And when the model complexity is very high, training sample prediction error is very low, but test sample prediction is very high. What is this? Overfitting or underfitting?
Overfitting.
This is overfitting. Right? You see, the model complexity is very high. That means it is overfitted with data. And when overfitted happens, the prediction error for training sample is very low, but test sample is very high. We have seen this example before in our previous classes. Okay, just try to remember that when the model complexity is very low, it's basically overfitting, and it's very high, it's overfitting. So we do not prefer either of them. We prefer somewhere in between, right?
When the complexity is high, what is when model complexity is low?
Yes, your question is when the model complexity is high and when the complexity is low. That is your question? Okay. Let me tell you that
model is complexity.
When the model is
yes, model complexity when it's low. Yes.
When there is not enough data to train the model, or when there is very limited rules, and the model has not, there's limited scope to train the model, then the complexity is low. You got it? There's very limited data to train the model. You got it?
Model complexity is low.
That is, the model complexity is low. And when the model complexity is high, when
model
it's overfitted the data.
It's overfitting. Model complexity when it's low.
When the model tries to consider when the model complexity low, it is underfitting.
High means overfitting.
High means overfitting, right? You got it, Abdullah? Abdullah, can you hear me?
No, not sir yet. Well, I'm very confused. Model complexity when model complexity is low, overfitting or underfitting? Yes.
Then it is underfitting. Model complexity low, it's underfitting. Model complexity high, it's overfitting. I have posted it in the chat box. Did you get that?
I get it. Thank you.
Okay. And complexity basically depends whether the model actually able to find the true relationship between its attributes. You know, the dependent attributes with the independent attributes, whether it is able or not. When it is unable to determine the true relationship, that means it misses lots of the rules, that is underfitting. And if it is makes too many rules than the required number of rules, then it is overfitting. You know, when it considers all the possibilities, all the exceptions, it tries to cover all the exceptions into rules. That means maybe it requires 10 rules, it is making 15 or 20 rules, then it is basically overfitting. Right? So I think we are having some praying time now. So can we give a break for 10 or 15 minutes?
Yes, sir. 15 minutes would be great.
Okay. So let's come back at 7:05. Come back.
Assalamu alaikum, sir.
Okay, are you back? Can you start?
Yes.
Okay.
Yes, sir.
Let me share the screen. So in terms of supervised learning, we discussed this earlier, the two types. One is classification, one is regression. It is for continuous value, then it's regression, and if it is for discrete values, if the target function has discrete levels, then we typically use classification, right? And in terms of classification, most of the classification models, they typically follow the same pattern. It's basically two steps. One is model construction and second is model evaluation. Yeah. So what happens in model construction? We basically train our model using a suitable algorithm. That is the model construction. And in the second phase, we basically do model testing. Because when you build a model, we have to test the model that how good it is. Okay? So for that, we reserve some data for testing. And using this testing data, we basically evaluate the accuracy of the model that we have built. And there's another phase that is model use, that when we evaluate the model with the test data, so depending on the accuracy, we can decide that whether we can use this model in the real world or not. Okay. For example, you prepare a very good dish at your home. So after making the dish, you test it, right? Before giving it to your guest, you basically test it whether the dish is good or not. If the dish is good, then you deliver it in front of your guest. But if it is not good, it is not edible. So, and do you think that you will give it to your guest? The food?
No, sir.
No. So in terms of models, we do the same kind of thing, and that after getting the accuracy, we basically decide whether we can apply it in real world or not. So that phase we are basically calling it model uses. Yeah. This is basically model uses. So we have a typical scenario here. Typically, we get a data set, a single data set, but we divide the data set into two parts, one for training and another for testing. So what happens with the training data? We apply an algorithm. So here comes the different models. We can apply decision tree algorithm, we can apply SVM, we can apply neural network, we can apply night days. So whatever models whatever algorithms we apply on this training data, it basically learn. It learns from this data, and we get a model, right? So to evaluate this model, we basically use the test data, that how good the model is. Okay. So in the beginning, the class levels are known for all these 15 data, right? This one as well as this one. But when we evaluate this model, we take out this data, take out these decisions, and we ask the model to evaluate these. So model gives a particular answer for each of these data points. Then we compare with these answers with its original class levels. That was in the beginning. Got it? So then after comparison, we can understand that how many yes the model is saying yes, and how many no the model is saying no. Then we can come up with some accuracy that out of 10 yes, the model is saying 8 yes. Okay. Out of 10 no's, the model is saying maybe 7 no's correctly. Does it make sense? You got the point? How we are evaluating the model?
Yes, sir.
But the important thing about before applying this algorithm, the data may contain some issues, right? It could have outliers, it could have noise, it may have some redundancy. So if we do not clean our data and you apply the algorithm, we will not get a good model, because the learning will not be good, right? Because if data has problems, issues, and if we apply the algorithm, the model will not be good. So what we have to do, we have to clean the data. So what does it mean by cleaning the data? If there's some missing values, we have to take care of it. If there's some noise, we have to remove that. If you have some outliers, we have to remove outliers. If we have some redundant data, then we have to take care of it. Otherwise, we will not get expected outcomes. Get it? So classification techniques, there's quite a few, as we have discussed earlier. So we have an example here. There's an example problem. For example, you have gone to a restaurant, but there is no table empty. All the tables are occupied. Get it? So now the question is whether you will wait in that restaurant until a table gets free, or you will move to another restaurant. That is a decision you have to take. Okay. Now you're thinking about some parameters. Let's say you're thinking about these 10 parameters that will help you to decide whether you will wait in that restaurant or you will go to another restaurant. Got it? So you have some attributes like alternate. Is there an alternate restaurant nearby? If there is an alternate restaurant nearby, you're asking yes or no. Okay. Bar. Is there a comfortable bar area to wait in? Friday, Saturday. Is today Friday or Saturday? Because you know, when there is Friday or Saturday, that means there is very limited chance for a table to get free, right? Because typically in foreign countries, Friday and Saturday is their weekly holiday, so it's typically overcrowded on these days. Hungry, the level of your hungriness, how much hungry you are. If you're too much hungry, then it's very little possible that you will wait here. If you're not hungry, then you may wait. But it depends on all the parameters here. We have patrons, we have price, we have raining, we have reservations, we have types, we have wait estimate. How long you have to wait, that's sort of estimation. Just think about that a single decision that you will wait in the restaurant or not is depending on these 10 parameters. And all the parameters is important, isn't it? All the parameters are important to you. And to help you to make a single decision is depending on 10 parameters. Just think about it. So in real world, we have data set that contains hundreds of like this, hundreds of attributes like this. That is affecting to in taking decision. Clear? Okay. So we have a data set here. We have some attribute, and we have the target attribute here, whether you will wait or not. So can you tell me that which attributes are the independent and which one is dependent attribute? Can you tell me? This target attribute, this is also an attribute, right? So which one is independent and which one is dependent? This normal.
The target maybe are dependent and others are independent.
Okay, what about rest? Are you agree with this?
So other than the target attribute, the others attribute can be dependent on each other as well. Like an example, if we see the weather data, the humidity can be dependent on the temperature. Like
but in terms of this one, typically what happens?
Sir, here day is the independent attribute, you can say.
Yes, these are the basically independent attributes, and target attribute is typically dependent attribute. But sometimes in the independent attributes, one attribute may affect the other attributes. That is also possible. Clear? That is also possible. But typically, these are the independent and the target attribute is dependent. Okay. So if I apply the decision tree algorithm here, we get some sort of tree like this. You see? Now, if you notice that who is in the root of the tree? All the nodes here are basically these attributes, right?
Right, sir.
And in the terminal level, leaf level, who are they?
Target.
Target value or decision, right? True or false? You see?
Right, sir.
In the internal level, internal nodes, all are attributes. But in the external nodes, in the terminal level, all are the decisions. Did you notice that? So you will get such kind of tree if you apply decision tree algorithm. Okay. Now the question is, you see who is in the root of the tree? There is an attribute that is in the root of the tree, right? That is which is patrons, right? Now my question is, why patron is here? Why not other attributes is in the root? Do you have any idea of that? Or who should be in the root? Decision tree.
Who is the more importance should be at the root?
Importance in terms of what?
So dependency. Which is more independent should be the root.
No. Not like that. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 attributes and 1 target attribute. So out of these 10 attributes, which one should go in the root?
The categorical attribute?
No. All are categorical. This one is also categorical. This true, false. Isn't it categorical?
Right, sir.
These are also categorical. Type is also categorical. Isn't it? Okay. So let me tell you the answer, that the attribute which has the which affect most in taking the decision of this target attribute becomes the root. Okay. The attribute which has the most influence on making this decision becomes the root.
So how do you measure that?
How do you measure that? That is the question. We have some formula, and we'll see some formula that helps us to determine that which attributes is influencing the most in making this decision. Okay, all the attributes has influence. There is no doubt. All these 10 attributes has some influence on this target attribute, but which one got the most? That is the question, right? So to do that, we have some formulas. We have entropy, and we have some calculations that help us to determine that. So we'll just try to have a quick look at that. So some basic discussion. Decision tree is a kind of greedy algorithm strategy. And iteration, it has a certain number of iterations, and it has some stopping condition that when we stop growing the trees, that sort of things. If you just go through this, it will be clear to you. Okay, now before that, when I apply decision tree, there is some condition that your data set should be categorical or discrete. You see, in this data set, is it categorical or numeric? This data set? And for that?
Categorical.
Categorical, right. But we have some numeric data here, right?
Right, sir.
We can see some numeric data. But price, what about price? Is it categorical or numeric?
It's categorical.
How can it be? How can
because
price
sir,
be categorical?
because sir, there are no. I mean, it could be $3 tag or $1 or $2. There are no price range here.
But there is price. If it is $3, 3 is a numeric, right? 3 cannot be a category. If
Yes,
it is
it's numeric.
1, it is numeric, right?
Yes.
I thought, sir, $3 sign means high, and $2 means low, or $1 means medium, and $1 means low. I thought that.
And that's true, but there is a price, right? You are right. You are right in a sense. But my question is, in the data set, there could be mix of that, categoric and numeric.
Right, sir. Mix of that. It's possible.
But if you want to apply decision tree, there cannot be any numeric value. If there is a numeric value, you cannot apply decision tree. You will not get correct answers. If there is any numeric value, you have to convert. You have to convert the numeric value into discrete values. Okay, then you can apply decision tree. For example, this last attribute you see, EST, it had numeric value before, right? Then what they did, they basically tried to make it discrete. How? They are making it as a range from 0 to 10. It is a range. 30 to 60. It is a range. You see, now it has quite a few levels. 1, 0 to 10, 1, 30 to 60, 2, 10 to 30, 3, 4 categories, right? 4 ranges. We have 4 ranges here. Did you notice that?
Yes, sir.
So now this is discrete. Now this is no longer numeric. Now this is, by applying ranges, we are making it discrete. This is called discretization. This process is called discretization. So now we can apply decision tree algorithm here. Okay. So our target was, same thing happens here for A's. It was numeric before, but we are making it range. We're making it discrete. Okay. How we know that which attribute will be the root. These are simple examples here. So let's just go through these. Okay, there's something to understand here. For example, you have a data set in which the target attribute has 2 levels. How many levels?
2 levels.
2 levels. For example, class 0 and class 1. Now, imagine class 0 has 5 samples and class 1 has 5 samples. So if its scenario is like this, we can term this data set as a heterogeneous data set. Got it?
Sorry, sir. Can you repeat, please?
If the class levels are equally distributed. For example, in a data set, you have 10 10 data points. Clear?
Yes, sir. Clear.
And in the class level, there are only 2 levels. For example, yes or no. Okay? And out of 10 data points, if the class levels are equally distributed, what does it mean? That means out of 10 data points, 5 data points has yes class and 5 data points has no class. That is, they are evenly distributed. Then we term the data set as heterogeneous data set.
Okay,
Yeah.
sir. Understood.
But if it is not like that, for example, one class got 9 data points and another class got only 1 data point, then we refer the data set to homogeneous data set. Got it? And if
Sir, if it's 6 versus 5, then it should be homogeneous or heterogeneous?
It's some sort of mixed, it will depend, you will make it some percentage, right? That means I am saying it is completely heterogeneous or partially heterogeneous.
Oh, okay.
So
Understood.
you have to term along that way, right? But the thing is that if one class got most of the data points and another class is very limited data points, then we have class imbalance problem. That is a very well-known problem in machine learning or data science. There is a class imbalance problem. If the data set is homogeneous, then we will face this kind of problem. Yeah. So in terms of learning, I would like to ask you a question: that which type of data set is good in terms of learning? Heterogeneous or homogeneous in terms of learning? You apply a model, machine learning model, and if the model learns from heterogeneous data, it will learn good, or if it learns from homogeneous data, it will learn good. What do you think?
Sir, I think homogeneous would be good.
Like, sir, homogeneous can learn better
Why?
because this is a similar kind of data, and machine can understand their what is it? It's their property and can make a better decision.
But if you notice, how many classes are there?
2.
2 classes. When you want your algorithm to learn from data, you are expecting that it will learn for the both of the classes, not only one class, right? Did you get that?
Right, sir. Right, sir. For both of the classes.
You want your algorithm to be learned for the both of the classes, not only one class. But you see, class 0 has 9 data points, and you can easily imagine that there will be very good learning for class 0, but class 1 has only 1 data point. Do you think that your algorithm will have a good learning in terms of class 1? Because there is only one data.
Sir.
No. But what happens here? You can assure that for both of the classes, the learning will be good or even. Clear?
Clear, sir.
Because if you want to achieve some sort of learning, you should have some data, right? If there is very limited data, then for that particular class, your learning will not be good. You get that? Okay, I think you have understood well. So now our point was that how we can understand that which attribute should go in the root. So there is quite a few methods. The first one is information gain. So we can use this method, information gain. There's some formulas here that we can apply on each of the attributes, and we can get some value. Whichever gives you the highest value becomes the root. So there is information gain. And we have Gini index. There is another method to determine the root. It basically depends on error rate. And we have some misclassification error. It's another method. So let's quickly see about information gain, how we can determine information gain. So to determine the information gain for all the attributes, we have some formula. What is the formula? The formula is this one. You see, gain A for attribute, for a particular attribute. If you want to calculate the value calculate the gain of a particular attribute, the formula is info D minus info AD. What does it mean? Info D, had D for data set. The info is some sort of entropy that you're going to measure. And info A, that in terms of that particular attribute, what is entropy? So this formula is basically this one, ID. You see? ID is basically entropy, and this one will be this one. The same thing. Here is I, they have written I, and here is info. The same thing, this formula. And info AD, the formula is this one. Okay? Get it?
Sir, I think we cannot see your cursor.
You cannot see?
I cannot see.
Okay. It's a little small, but I am moving it. I'm moving around. Can you see it?
No, sir.
Is it better now? You see my mouse
Yes.
now?
Yes, sir.
Now I brought it here. Can you see it now?
When it's in the slide, it's difficult to see, but in the dark area, it's easy to see.
Yes, because when it's in the slide, it becomes smaller and very big. Okay, very thin line, so it might be. But it has one formula mainly, and it's elaborated here. You see the expected information, you see? This is the basically entropy. Entropy of the whole data set, 80. And another one is the entropy in terms of a particular attribute. If we difference these two, then we get the gain for this particular attribute. Now let me explain what is entropy. Is there anyone, you know, have you heard this term before, entropy? Do you know what is it is about? Anyone?
Sir, can you repeat the question, please?
Entropy, what is entropy? Have you heard this term before?
Yes, sir, I have heard it in physics.
In physics, yes. In physics, there's a term called entropy. But here, in terms of data set,
Sir,
what is entropy?
say in decision trees, I guess when our tree becomes too much messy, or if we have too much data and if it takes too much long time to generate, then we get too much entropy.
No, it is not like that actually. It has no connection with physics. It has a different meaning. You see the heterogeneous and homogeneous example?
Yes, sir.
So for heterogeneous example, if we calculate the entropy for this data set, we get 1. Got it? And if we calculate the entropy for this data set, we get a value close to 0. It would be totally 0 if it is 10 and 0. Did you get that? So the value
so are we
of,
dividing it?
so the value of entropy is ranged from 0 to 1. When it is 1, when all the class levels are evenly distributed, then the value of the entropy is maximum 1. But if it is imbalanced, then the value of the entropy is close to 0.
So basically, sir, entropy refers to the ratio of data points to the nodes, right, sir?
Ratio of the class levels.
All right, sir.
Class levels. If it is evenly distributed, that means heterogeneous. If it is completely heterogeneous, then we get maximum entropy 1. If it is completely homogeneous, we get the lowest entropy, that is 0. Got it? So if we apply this formula, we basically get that. Now, what this formula says? This is kind of summation. I equal to 1 to m. And what is m? Can you tell me? Anyone tell me what is m? The summation is over I to the 1 to m. What is m? This m is
So number of nodes,
number of classes.
classes.
Number of classes. If there is 2 class levels, then m is 2. That means we'll get 2 terms like this, minus this one, minus another term. If there's yes and no, so we'll get 1 term for yes minus this one, and another term for no minus for that one. Get it? If there are 3 levels, then we get 3 terms like this, minus this, minus this, minus this. Yeah. And what is p? P is just the probability. Okay. How we calculate that? We know that how to calculate probability. So if for the first time, if it is for yes, 1 class, then we measure the probability of yes in the whole data set. Then minus, if there's another class for no, we measure the probability of no in terms of the whole data set. Okay. The same thing happens when we calculate the entropy in terms of a particular attribute. This one is for the whole data set, this one, the ID. And info AD, this is also entropy, but this is not for the whole data set. This is for a particular attribute, which is A. So if you have 10 attributes, we have to calculate this. We have to calculate this equation. We have to apply this equation for all 10 attributes. But these will remain the same, ID. These will remain the same for all the attributes. Okay, then we get gain. We get gain.
Okay. Sir, can you please explain the info AD again, please?
Info AD. Yes.
Right.
Info AD is similarly, it has minus, but it doesn't has any minus. It is positive, and it is termed as j equal to 1 to b. What is b?
So number of classes.
Number of labels in that particular attribute A. Got it? So in terms of ID, for the whole data set, the M was number of class levels only for the class attribute or target attribute. But when it is info AD, what is V? V is number of levels only for that attribute. For example, let me give you an example. The data set, where is the data set? Okay, you can just pick it here from here. For example, I'm talking about, I'm calculating the entropy for S attribute, right? So if I calculate the entropy for S attribute, how many levels are there?
So 3.
3 levels are there. So the number, so the value of V will be 3 here. Did you get that?
Yes, sir.
Yes. So that's what we are saying here. So here V will be the number of levels for that particular attribute for which we are measuring the entropy. Clear?
Yes, sir.
Okay. And what is this? dj and d? These are the probability. This is basically probability. This you can term it as pj. Here they have written only pi, but this is basically pj. So we do probability like this. Okay, multiplied by I dj. We'll have example that it will be clear to you how we can calculate. You see, for information gain for patron attribute, they have calculated these. They are saying that the entropy for the whole data set is 1. But waiting in the restaurant, that data set, the entropy is 1. And when the entropy of a whole data set is 1, can anyone tell me? We just discussed this here. Here.
When it's non-homogeneous or evenly distributed.
When it is heterogeneous. Okay, can you just quickly go back to the data set and see whether it is heterogeneous or not? Not this one. This one. Can you count how many levels are here in the class level? Class attribute. How many levels?
Sir, 12.
No, I don't know
Levels, sir,
how many?
Two, sir, 2.
2 levels, true and false, right?
Yes, sir. 6 true, 6 false.
Now, can you count how many true and how many false?
Sir, 6 true, 6 false.
That means whether is this data set heterogeneous or homogeneous?
Heterogeneous.
Heterogeneous. It is 100% heterogeneous, isn't it?
Yes, sir, 100%.
If it is 100% heterogeneous, what should be the value of the entropy for this whole data set?
So 0.5.
1 maximum. Get it? It will be 1. If we apply this formula, you will get it 1. We do this. So that's why they have written 1. Why they have written 1? Because in the gain formula, info D, first of all, I have info D. So info D is 1. Then info AD, that calculation is this one. Info AD, this one. So here A means attribute. So here we are calculating the information gain for patron attributes. And then we are calculating the information gain for type attributes. So they have shown the information gain for 2 attributes. Okay. So do you understand this calculation? It's basically from this formula. There is nothing else. If you just follow this formula, you'll get these values and you will get these results. So the information gain for patrons, we are getting 0.05, and for information gain for type attribute, we are getting it 0. For type attribute, can you tell me why you are getting it 0? Information gain for type, why you are getting it 0, the information gain?
So this is because the entropy is 1 for type.
Entropy is 1 for type. So can you go to the type attribute, just have a quick look and see whether now we have, yes, under type, how many levels are there on the type?
So 12.
How many different types? I mean,
4,
unique.
I guess.
4, sir, 4.
4. French, Thai,
Thai,
burger,
burger,
Italian.
Italian.
4. Now tell me how many French is there, how many Thais are there, how many burgers are there, how many Italians are there?
2 French, 4 Thai, burger,
2 Italian.
4, and 2 Italian.
Mhm. French, how many French? 2 French.
2 French,
And how many Thai?
4. Burger, 4, and Italian.
Okay. 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 That means you have to calculate basically for all these 4 different levels. So when you put it in this equation, so the value of V will be 4, right? Because there are 4 different levels. So how many terms we'll get like this? We'll get basically 4 terms that will be sum up, and we get it for type. Okay. You just try to try these calculations, these formulas. If you still have problems, then we can have further discussion. It's just from the probabilities, nothing else. It's those class levels, the probability of those class levels. Okay. Now you see, when you calculate probability, we basically divide into the total number of data points. So how many data points were there in the data set? 12, right? So you see all the terms are divided by 12 here. This 12, this 12, this 12. Okay. And what is this 2? This 2 is a number of occurrence for a particular level in the data set. For example, patrons, how many levels the data set for patrons, how many levels? I think three levels, right? Because we have three terms here. This one, and this one. Three terms, isn't it?
Yes, sir.
Yes,
Three
sir.
terms. Now, the first level, for the first level, we are writing 2 by 12. That means first level appears 2 times, and the second level appears 4 times, and the third level appears 6 times. So that's why 2 by 12, 4 by 12, 6 by 12. We can check that for our confident. For the patrons. Patrons, how many levels? Some, full, and none, right?
Yes, sir.
So how many sum are there?
Sir, 4.
4. That means for sum, the probability will be 4 by 12, right? 4 divided by total number of data points. For full, how many fulls are there?
1, 2, 3, 4, 5, 6.
So for the probability of full, it will be 6 by 12, right?
6 by 12. Yes,
for,
sir.
for none, how many nuns are there?
2.
2. For the probability of none, it will be 2 by 12, right?
Yes, sir.
So 2, 4, and 12, right? And we got exactly the same here. You see, 2, 4, 6. Clear?
Yes,
And
sir.
this is dj by d. This 2 by 12, 4 by 12, 6 by 12. This is basically dj by d. And there is another term along with it, that is idj. How we calculate the idj? You see, we calculate id here. If we know how to calculate id, we know how to calculate idj. The same formula here. The same formula. You just have to apply the same formula. Okay. So I want you to try it at home. Then we can discuss further in the next class. If you still have problem, if your problem persists. Okay. So how you know that which one is the root? So they have shown the calculation for 2 attributes. So if I know how to calculate the information gain for 2 attributes, I know how to calculate it for the rest of the attributes, right? So if there are 10 attributes, I have to calculate the information gain for all the 10 attributes. Then I get these values. Which one is the maximum? Become the root. Very good. So among these two, patrons and tide, which one has the highest value?
Patrons.
Patrons. So if we compare these two, so patron got the highest value, so it becomes root. But we cannot decide until and unless I calculate the information gain for other attributes. Now we got only the root, but you may question that after calculating all these information gain, we know what is the root, but the tree is not only with the root, right? Tree has to extend. So if the root is patrons, then what next?
So the labels.
The process is same. The process is same, but with the data set will be different. I mean, the same data set, the master data set will be same, but with sub data set there, it will work with on sub data set and decide which one will be the in the next root, then next root, then next root. When we got all the attributes in my tree, then I know that I have to stop now. When all the attributes is in the data set, I know I have to stop now. Okay. This is a one method using information gain. There is another method, Guinea, and there is an error-based method, but we are skipping it for now. We'll try to understand the information gain and how it works. I can give you some other materials that might help you to understand it better if the calculation here is not clear to you. Okay. Do you have any question from here? Please feel free to ask. Would you like to ask any question?
Sir, so the leaps for the decision tree will be arranged by the values of gain in decreasing order, right, sir?
Sorry, can you repeat?
So after we finding the roots, sir, we will extend that decision tree by the decreasing order of the gains value, right, sir? Like
No. It is not like that. It is so first time we will calculate the gain for all the attributes, right? Which one is the highest? It becomes the root.
Okay, sir. So then, how do we find the next child?
How do you find the
child
next one? That is the question. For example, this one. Let's see this one. You see, we have 1, 2, 3, 4. We have 4 independent attributes and 1 dependent attribute, that is a class level, that is Bayes computer. And here they're saying that age is the root. Just imagine that age is the root. Okay.
Okay.
So under age, how many levels are there?
So 3 levels.
3 levels. So if age is the root, it will have 3 hands because it has 3 levels. And it will have 3 hands. Clear?
Yes, sir.
So what are the hands? Let's say one is youth, one is middle-aged, one is senior, right?
Yes, sir.
Now, if it is middle-aged, you see it is yes. That means there is no variation, only one class, yes. If it is middle-aged. Clear? For example, let's say middle-aged is 31 to 40. Now, if you check 31 to 40, all are yes. 31 to 40, yes. 31 to 40, yes. 31 to 40, yes, right? So if it is middle-aged, I will directly go to the decision, yes. So from this end, the tree will not extend. Did you get the point? Because if it is middle-aged, all the times it is yes. It doesn't depend on other category, income, student, credit rating. If it is middle-aged, the target value is always yes, same.
Yes, sir.
It is not depending on this. So the tree will not extend here. But in terms of youth, it has both classes. It has yes, it has no. That means there is option to grow the tree. In terms of senior, it has also mixture, yes and no. But there is option to extend the tree. Did you get it? Now you may question that, okay, I understand that for middle-aged, it will not extend. For youth, it will extend. But for youth, which one will be the root node here?
Yes, sir.
Right? Which attribute? Because age I already got, but there are other attributes: income, student, credit rating. Among these three, which one will be here? That is the question, right? So how we get that? We determine the information gain for income, student, and credit rating again the same way we followed in the first time. Again, we have to measure the information gain, but data set is different now. Which are the data set? Youth. Who are the youth? For example, less than 30. So how many data points are there? Less than 30. If we consider them youth, 1, 2,
Five
3, 4, 5 data points are there for youth. So now I will calculate the information gain only with these 5 data, not all the data. Information gain of these 3 attributes, right? Only with these 5 data. Which one is gives the highest information gain among these 3? Only for these 5 data becomes the root here. Did you get the point?
Understood, sir.
So it's same for all the attributes. For senior, how many data we have? Senior greater than 40, 1, 2, 3, 4, 5. Again 5. In the same way, we will calculate the information gain only for these 5 data among the rest of the attributes. And which one gives the highest information gain becomes the root here. So it will continue like this.
Sir, so basically the data set will be shrinked along with the extension of the group tree.
Exactly. The data set will be, the amount of data will be decreasing as we expand the tree.
Right, sir.
Right?
Yes, sir.
So this is the overall idea. I request you to try it at your home. If you face any problem, then you can discuss it further in the next class. If you have any more question, you can ask. Okay, I believe that you got it. And
sir, what is Guinea? I lost the connection. What do you say about the Guinea?
Guinea or gain? Are you talking about Guinea or gain?
Guinea. I don't see now.
Guinea. Okay, Guinea is another method
down
through which we can also calculate the root, but it is depending on error. Information gain is basically which one gives you the maximum value becomes the root, but in Guinea, which one gives you the lowest value, that means lowest error, becomes the root. But for today, we have skipped the Guinea method. We have only discussed the information gain today. Yeah, thank you so much. I think we can stop it for today, and we'll have some other discussions in our next class. But before the midterm, we will have a class test like this, like the pattern we'll follow in our midterm examination. We'll have a class test. I will declare you the date, and we'll have an assignment also before the midterm examination. We'll have a class test and an assignment before the midterm examination. I will inform you the detail about that. Okay.
Okay, sir.
Okay, thank you so much. So we'd like to wrap up for today. Stop the recording. Thank you so much.